Hello all, welcome back. We've got the sort of second half of this session on methods and method development, and we've got three talks here over the next hour before our lunch break. So let me just start by introducing Manis Sharma, and he'll be talking about density functional embedding scheme for molecules in periodic systems coupled with wave function methods for and real-time dependent time dependent density functional theory. So Manis, the stage is yours.
Hello everyone, thanks for the introduction. So I'm a PhD student and welcome to my talk. So I'm developing and implementing density functional embedding theory within the TurboMole program package that employs Gaussian type basis functions. The implementation is coupled with wave function theory methods like model-placid or coupled cluster methods like CCHDT. It is also coupled with real-time time-dependent density functional theory or RTT-DFT. So what is this density functional embedding theory or DFED? Well, in a nutshell, it allows us to treat a small portion of a system using a high level of theory that is computationally expensive and more accurate, while the remaining not so important system can be treated using a lower level of theory that is not so computationally demanding. Due to these reasons, DFED finds its application in the study of hybrid systems such as solvated molecules or a molecule adsorbed on a surface. In such systems, the focus of study or the region of interest is only maybe the molecule or maybe a few atoms around it. And most of the times, the periodic surface, that is the environment, can be treated or described well using a lower level of theory like LDA or GGDFT. The cluster or the molecule, however, requires a high-level treatment via wave function theory methods or a hybrid density functional theory. If you decide, however, to treat the entire system using LDA or GGDFT, then you will get large errors in local properties like adsorption energy of the cluster onto the surface, or maybe the excitation energy of the clusters. On the other hand, if you decide to do CCHDT for this periodic system, then actually it would be computationally prohibitive. And not only that, it is also not really needed. You may still be able to perform a periodic hybrid density function theory calculation, but yeah, as I said, writing an efficient and periodic CCHD code is not so straightforward or practical. So these are some of the issues that we are dealing currently. Furthermore, the periodic boundary conditions lead to unrealistic surface coverages, and one requires really large supercells to address this issue. The solution to all these problems is provided quite naturally within the framework of density functional theory, where the properties of the system are determined by the electron density. Therefore, it allows us to partition the density of the total system into a cluster and an environment density, and the influence of the environment onto the cluster can be taken in the form of an embedding potential that is a function of both cluster and environment density. Various strategies to construct the embedding potential have been implemented, and to understand them, let us consider a model system where I consider the benzene molecule as my environment and the water molecule as the cluster that is the region of interest. So in the method 1, what we do is we relax the environment density, and then we plug this environment density into the embedding potential, and then we relax the cluster density in the presence of this embedding potential. This method is actually approximate in nature due to the presence of non-additive kinetic energy density functionals within the formula of the embedding potential. Just like the exchange correlation term, the exact form of the kinetic energy density functional is not really known, and you cannot really get exact results. The second method, what we do is we take the total, we relax the total density of the total system using a lower level of theory like LDA-DFT, and then we subtract the isolated cluster density, also determined using the lower level, for example, LDA-DFT, and then we take this subtracted or this difference density as our environment density, and then we plug this environment density into the embedding potential, and then we relax the cluster in the presence of this embedding potential, just like the method 1. And again, this is approximate in nature due to the presence of those non-additive kinetic energy density functionals. The method 3 is pretty much the same as the method 1. However, here the use of the approximate kinetic energy density function is avoided by using a projection operator that basically orthogonalizes the quantum orbitals of subsystem A with respect to the orbitals of the subsystem B, or vice versa. And this basically means that this method is exact in nature. So to sum up, I would say that method 1 and method 2 can be used for weakly interacting systems, while method 3 is suitable for even strongly interacting systems. Furthermore, it is quite common to perform a freeze and thaw procedure where the roles of the environment and the cluster are interchanged iteratively until self-consistency is achieved. So enough about the theory. Now let's have a look at the kind of results that you can expect in practice. For that, I will show you some ground state properties obtained using molecule-in-molecule DFT. So here are some molecular binding energies, and please bear in mind that these are just DFT in DFT embedding energies. So these only serve as a benchmark, and you cannot get as better than DFT. You can only get as good as DFT. So if we consider the method 1 and some weakly interacting systems like the water dimer or the HF dimer, then you will see that the method 1 gives reasonably accurate binding energies compared to the green reference DFT binding energies. And if you employ freeze and thaw as well as supermolecular bases, then you improve this results even further. However, for strongly interacting system, for example, this ethane molecule that have partitioned at the carbon-carbon covalent bond and form the CH3 positive and CH3 negative subsystems, you will see that we are getting really huge errors compared to the reference calculations. However, with method 3, we are able to reproduce the exact binding energy from the DFT for either weakly or strongly interacting system. We have also implemented periodic and periodic density function embedding theory using the method 3. So here we are able to reproduce the exact total ground state DFT energies. As you can see over here, the errors associated with DFT are of the order of microhartree. The system considered here are, for example, a polyethylene 1D periodic chain, neoprene 1D periodic chain, or a 3D diamond crystal. And the implementation also supports multiple K points. And what we did was basically we considered the labeled atoms, for example, these 3 over here, or these 4 over here as our one subsystem and the remaining as the other subsystem, and employ the projection operator based embedding. Now, till now, we have seen only DFT in DFT embedding, so no real improvement over the DFT description was observed. Now, I will show you some results for molecule in periodic DFT, which was coupled with CCSGT, that is the wave function theory method. For that, let us consider a system of H2 molecule and an H10 1D periodic chain. And here I have plotted the absorption energies of this H2 molecule on this chain for various separation distances obtained using LDA in orange and CCSGT in blue. Of course, you see that the LDA description overbinds the H2 molecule as well as predicts too short equilibrium distance. Now, if we perform DFT by considering the H2 molecule as well as the 2 atoms within the H10 chain as the cluster, that is the region of interest, and perform the embedding, or rather construct the embedding potential using the method 2, then you notice that this green curve here that corresponds to CCSGT coupled with DFT is now much closer to the regular CCSGT result. So this is really incredible because the computational cost is pretty much largely reduced, because we are only considering these 4, the basis functions on these 4 atoms for the CCSGT calculations, and the remaining are treated via DFT. Now let's have a look at some excited state properties with DFT obtained by coupling with wave function theory methods as well as with real-time time-dependent density function theory. So first, let me show you some CC2 DFT excitation energies of solvated molecules such as methylene, cyclopropene, acrolein, and acetone. So in this table, we see the first excitation energies of the 3 molecules. When we run a CC2 calculation on the entire system, those are in the green column. So these will be our reference excitation energies. And then if you look at the errors associated with different methods, you notice that method 1 performs really great with only a maximum error of 0.03 electron volts. And this is pretty interesting, as when we also employ freeze and thaw, then actually the results get slightly worse. So this means that there's some kind of error cancellation happening in the method 1. And the method 2 actually performs the worst. It's still not that bad, but of course, if given a choice, we'll pick up the method 1 anytime. Now, let me also show you some RTTT DFT results. For this, we are considering a system of 2 interacting chromophores, such as a benzene fulvene dimer at a separation of 4 angstroms. And in the purple curve, basically that is the RTT-DFT absorption spectrum obtained when you run the calculation on the entire system. So that would be our reference curve. And the green curve corresponds to the DFT with the method 3, that is the projection operator, the exact method. And you can see that the DFT absorption spectrum is able to reproduce all the major characteristic features of the reference spectrum. And what we basically are doing in this is that we are considering the benzene as the cluster and then the fulvene as the environment, and then vice versa. And then we have plotted the spectrum. And also the minor differences that you are seeing are because while evolving the electron density of the cluster in real time, in the presence of this external electric field, the environment density is actually being kept frozen to the ground state density. And that is the reason that you get these minor differences. Secondly, if you employ the approximate method 1 for the construction of embedding potential, you see that while the peak positions are still slightly predicted up to some reasonable accuracy, the intensities are all messed up, and that is also expected. And yeah, so in conclusion, I would say that the FET using Gaussian basis functions is actually a very promising tool for investigating hybrid systems, and we have been able to implement molecule in molecule, periodic in periodic, as well as molecule in periodic DFET using very efficient techniques. We have also seen that DFET coupled with wave function theory methods is able to improve the ground state as well as the excited state description of provided by LDA or GTA DFT. Furthermore, DFET coupled with RTT DFT also provides reasonably accurate absorption spectra. So where do we go from here? So currently, as I showed you, that the molecule in periodic DFET was working with method 2. However, we would also like to use the method 3, that is the exact method based on projection operator for it. And also, we'd like to investigate some nonlinear properties, such as the high harmonic generation spectra obtained using RTT DFT coupled with DFET for molecules in the presence of some nanostructures or periodic surfaces. So yeah, in the end, I would like to thank my supervisor, Professor Marek, for his continued guidance and support throughout. Also the NOA project for my funding, and the Turbomole for the development support. I would also like to thank the organizers for providing me an opportunity to present my work here. And thank you for your attention, and I'd be happy to address any questions.
Yeah, thank you, Manus, for your talk. We have time for some questions, and if folk can type some into the Q&A tab. We currently have one in there at the moment. Let's have a little look and see where we are. Can you choose a cluster space which is covalently bonded to the environment, or are there problems with this in practice? Presumably, for a wave function cluster calculation, you need to have a closed quantum system with integer electron number.
Yeah, so the trick, for example, with method 3, we can actually do it. But the trick that I applied was, since the implementation currently only supports closed shell systems, so I just used the, I provided a positive charge and negative charge here, so that both the systems are neutral, like closed shell systems, sorry. So CH3 positive, CH3 negative, and like this. However, for the molecule in periodic embedding, since that only works with the method 2, we cannot cut through covalent bonds there. I hope that answers.
It was actually very related to my question. I was going to ask if you could have charge transfer between the two different systems. I guess you've more or less answered that then, or do you allow for some sort of charge transfer if you've got a system where that may happen?
Yeah, that is interesting, because we also want to study charge transfer, and I have, so that is actually the next goal. And I have seen some papers addressing that using this technique, but yeah, it would be interesting. I'm not really sure about how that implementation works right now, but people have done that, because what we have is we have like localized molecular orbitals. So it would be interesting how to.
Yeah, definitely. We have another question has appeared. Thanks for the nice talk. Yes, thank you. For the H2H10 system, can you elaborate on why the DFET is better than full DFT? Should the DFT not be your exact limit to DFET?
Yeah, so for example, when in these two cases where, for example, we have these molecular binding energies as well as maybe I was not able to explain my concepts better, but in periodic as well as in this case, what I'm showing is just DFT in DFT embedding. So here, of course, the limit would be DFT. But for this case, what I have done is we have, so once we construct this embedding potential using just the DFT, then we take this embedding potential and put it onto the Hamiltonian for the CCSDT reference calculation. For example, we just put this embedding potential onto the Hartree-Fock potential and just perform CCSDT on it. So very like naively, without any much fancy theory, and it works quite well.
Oh, thank you.
I hope that answered the question.
Yes, thank you. Thank you very much.